Hello class. Today our topic is uniform flow. What is uniform flow? The flow in open channel is said to be uniform flow if its property remains constant with respect to distance. Which kind of property is this? Is that means depth of flow, area of cross section, and velocity of flow. These properties are constant with respect to distance or space. Now, the constant depth of flow, constant, suppose there is a bed and this is the flow which is constant throughout the length. This depth is called as normal depth here. This is the bed slope. You can find theta with the horizontal. This is y naught through its bed slope. This is bed slope, this is surface slope, and this is y naught is the normal depth. Because the depth is not varying with the distance, is called the normal depth. Now, as the depth of flow and velocity at every section, as the depth of flow and velocity at every section are constant, therefore the channel bed slope, surface, water surface slope, and energy line slope will be equal. That means all are theta. All are theta. All are theta. And in the uniform flow, the frictional resistance acting between the fluid and the channel boundary are balanced by the gravity. That means gravity force is dominating here. Uh, in, in this case, in this case, velocity of flow does not change with respect to space. So here acceleration will be zero. Hence, we can say the sum of component of all the external forces in the direction of flow must be equal to 0, because all external force F external force is equals to m into a. So here is acceleration is 0, so all the external force must be equal to 0. Equal to 0. Now for the Chase's equation, we considered a moment equation for uniform flow. We consider a control volume section. This is the control volume section. This is bed. This is bed. Which is inclined by theta from the horizontal. This is theta. Here is the control volume. Here is section 1 1 and here is section 2 2. The pressure is acting is P1 and pressure 2 is acting P here. So here is weight. Weight is W, is vertically downward, and this is inclined by theta, so it will be theta. So here W cos theta and here W sin theta. Now writing the momentum equation, and also here is frictional force F, acting between fluid and the channel boundary. Here now we considered control volume, and we can say P1 minus P2 minus FF. We are considering flow direction in this is the flow direction. V naught is the velocity of flow. So here P1 minus P2, where P1 in the direction of flow and P2 is opposite to the direction of flow, minus frictional force which is acting against the direction of flow because of the frictional force. W sine theta in the direction of flow, weight of the water or fluid in control volume, and which is equals to m2 minus m1. This is momentum equation in OCF for steady flow. So here P1 and P2 is same because the depth is not vary. So P1 and P2 are same. So they are equal. M1 and 2 are equal because there is no change in momentum because acceleration is zero, velocity is not changed. So M2 and M1 is same. So frictional resistance frictional force is equals to W sin theta. We know the weight is equals to gamma AL. That means density of water into cross sectional area into length between two sections from A to B. This is the length. So here W is gamma L sin theta, and frictional force which is equals to frictional resistance into T into L into V square. T is weighted perimeter of the channel and is length of the channel, and V is the velocity. This is the frictional force. We equating that this we put these values in here, so it will give V equals to CRS. CRS. Here is sin theta. Here is sin theta is S is the bed slope, which is angle is too small, so we can say it with theta. So here is a bed slope. Area upon perimeter, which is R. So root RS. This is RS, and gamma by F is root of gamma by F is C. This is the frictional factor F. Gamma is density of water. There is a change is constant. Now we know the loss, frictional loss is equals to FLB square by 2GD. So here we say FLB square by 2G into D. 2G into D. Here D is, we find out the D value for the section. So R is hydraulic mean depth is equals to area upon perimeter. So for area upon perimeter, so here is the area pi by 4D square, and this is pi D. So we will cut that for the circular section. So D equals to 4R. For circular pipe, D is the diameter. So here we put the value of D, which is equals to 4R. So HF, we transfer the value here. So here V equals to root of HF by L, or root of HG by F. So from this formula, V equals to C root of RS. We compare this. So here slope is root of HF by L. Slope is HF by L. slope HF by L, not root of HF by L. This is slope is HF by L, and C value is root of 8G by F. This is the Chase's constant for the circular pipe, and this C value for channel section, and this is for circular section. Okay. Now shear stress for OCF. Here is frictional force W sin theta, and shear force is shear stress into P into L. This is perimeter area, wetted area. So here equals to gamma L sin theta, which is equals to gamma R sin theta. This is the shear stress between wall and the loop. Now next one is economical channel section. A economical channel section is said to be economical when its construction cost is minimum for a given discharge. Okay. So here a section is said to be most efficient if for a given cross-sectional area the discharge carrying capacity is maximum. Now we know the E equals to CRS, C root of RS because of Chase's formula, and Manning's formula, B equals to 1 by N R to the power 2 by 3 S to the power 1 by 2. So here C root RS, there is a relation between C and N. That means Chase is constant N and Chase, Manning's constant N and Chase is constant C. This is the relation between them. So we here for most efficient, most economical channel section. So here discharge for the most efficient section, discharge capacity is maximum for the given area. So Q equals to area into velocity. So here we consider a Manning's equation. So 1 by n r to the power 2 by 3 raised to the power 1 by 2. So we put the values. R is the hurdle mean depth, so which is equals to area upon perimeter. So here 2 by 3 will be by about 2 by 3. Slope is same and area is same for the given area. So here discharge is varying with respect to perimeter. So we can say that the perimeter is minimum for maximum discharge for the given area. That is the condition for most economical section. Now for most efficient section for rectangular channel, consider a rectangular channel section with B and depth of flow Y. Here area is equals to B into Y and perimeter equals to wetted. That means wetted perimeter, not full perimeter. So here B plus 2Y is the perimeter. Now we can say B equals to A by Y. So here B equals to A by Y plus 2Y. For the minimum condition, we differentiate this term with respect to Y because A is constant or A is given. So here a variable is Y. So here we differentiate with respect to Y. So dp by dy equals to minus A by Y equals square plus 2 equal to 0. So here A equals to 2y square. We put the area here, so we can say B equals to 2y. B equals to 2y or y equals to 2 by 2. And the hydrogen mean depth is area upon perimeter. So here B by y divided by D plus 2y. Put the values of D. So here 2y equals to hydrogen mean depth equals to y by 2. For most efficient rectangular channel section, depth of flow y equals to D by 2 and hydraulic radius or hydraulic mean depth is equals to y by 2. Now next section is trapezoidal section, and one section is triangular and another one is circular. These four types of section we are using for channel section. First, the rectangular channel I have already seen. So here second one is trapezoidal section. We have first trapezoidal section in which when side slope is fixed, that means slope is constant, and side slope is varied. This trapezoidal section we will see in next lecture.